OK, so now we get into the fun stuff, out-of-order processors. Up to this point, we've been doing simple in-order stuff. We've been hinting at out-of-order, but now we're going to start looking at truly out-of-order machines. And we're going to introduce a bunch of new structures that you should not have learned about up to this point. You may have briefly talked about a scoreboard, but we're going to start talking about a bunch of other structures. OK, so let's talk about different portions of a pipeline that can be in order versus out of order. The front end. So what do I mean by the front end? The front end is instruction, fetch, and probably decode. This is pretty hard to do out of order. Because you want to know, I mean, unless you've actually sort of can predict the future, it's pretty hard to know. So most of the machines we're going to be looking at have the front end being in order. So I/O here means in order, OOO means out of order. Issue. So this is the stage in the pipe that actually says, all the operands are ready, go start executing the instruction. Well, so there are some things that can be in order, but you could probably even get more performance if you try to do that out of order. So probably not today, but next lecture we're actually going to talk about how to have the issue be out of order. Write back. So this is writing to something that looks like a register file, but not necessarily having hit the commit point of the processor. So this means that things are no longer in flight in the bypass network. It's been committed to a register file. I won't call it the register file just yet. Well, you can do that in order, out of order. Oh, excuse me, you can do that in order, out of order, different choices there. And then finally, commit. So this is saying, yes, I actually want these instructions to actually commit. And I'm basically, after that point, you're not able to roll back the machine state to a previous state. And we're going to look at machines where that's both in order and out of order. This is sort of a gentle introduction to out-of-order execution. And we're going to be building some different architectures. And this name here just is sort of a naming of 5 architectures we're going to look at as an introduction to out-of-order. The I4 is in, so or in order, in order, in order, in order. I2O2 is in order, out of order, out of order. Into out of order, in order is in order, out of order. It's the number just means how many stages in a row are the same as the letter before it. OK, so I want to briefly touch on some nomenclature over here. And you shouldn't know what these things are yet unless you went and read Shen Lepasti, which I highly recommend. Scoreboard. This is a structure where we keep information about what instruction is ready to execute. Reorder buffer sometimes gets merged into a lot of different meanings, but typically when we execute instructions out of order, this is a place where we can go and actually reorder them to commit them in order. And we resolve all the dependencies so we don't actually commit out of order. Store buffer. This is something where we'll actually hold off storing to memory until the commit point, because we don't want to write to memory too early, because that would be bad, because then that would effectively be committing. So yeah, this is one important thing to remember about commit points is if you commit too early, what is an important notion of a commit here? Well, it's any state that you can't roll back. So if you do a store to main memory, that's a commit. That's really hard to roll back, unless you somehow can keep all that state of what was in that memory location before that. But people typically don't do that. Instead, you'll actually sort of have a buffer which keeps track of all the stores you're trying to do. And every once in a while, when you actually do a commit of the instruction, at that point and only that point do you store to main memory. And finally, we'll be talking about the issue queue, which is if you are issuing out of order, this is a structure which allows you to determine when it's safe to go and issue an instruction or not. And this is what's important about this is it keeps all of the dependencies, the read after write, write after write, write after read dependencies in check. And that's what that structure is doing. So we're going to look at some of these structures today. OK, so a motivational code sequence here. And this is a motivation for out-of-order execution. Here's a simple code sequence. And let's take a look at some of the read after write dependencies for this code sequence. Here we have a write to register 1 and a read of register 1. So that is a dependency there. So instruction 0 has instruction 2 as a dependence. So we'll draw a nice arc there. Let's see what else happens here. Instruction 2 writes to register 5, and that gets read in instruction 3. So that's a dependency arc there. OK, interestingly enough here, instruction 1 isn't dependent on instruction 0, and instruction 2 and instruction 3 are not dependent on that. So we can just put in a separate little bucket here. Instruction 4 here, let's take a look. Register 12, register 11. It reads register 11. So it's dependent on instruction 1. 5 is dependent on the output here, 12. So it gets put after 4. And likewise, 6 reads register 12. So it is dependent. So we have to start to think about if we have an out-of-order processor, we can choose the order of this instruction sequence and that instruction sequence. And if we have a multi-issue or a superscalar out-of-order processor, we can even think about trying to execute these completely independently at the same time, and we can get performance from this. Because we can find parallelism inside of a sequential execution stream. So one important thing here to realize is today we're going to be talking about how to dynamically, in hardware, schedule this and this at the same time. And we're going to be using this as a motivating example. In the VLIW, or the very long instruction word lectures, we're going to be talking about some software techniques that can determine when to execute this and this at the same time, and architectures which can take advantage of that, where the software has determined that these two things are completely independent. OK, so an important thing to realize here is that why do these even happen? Why do we end up with sort of non-dependent instruction sequences in a program? This is like a philosophical question. Should this even, why is this possible? So what do in-order instruction semantics, or excuse me, sequential instruction semantics force you to do to instructions? Forces you to come up with an order. You need to come up with some order. I need to write it on a sheet of paper in some linear order, or store it in my memory on my computer system in some order. An important point here is that in the instruction set architecture of a sequential computer, by definition, the instructions need to be serialized. This is a limiter. This is a problem in sequential machines. You need to come up with some order. So there is no way to express that this and this can execute at the same time in a sequential in-order machine, or a sequential machine rather, unless you do it something like this. You need to come up with some order. Like this is expressing the parallelism, but it's hard. The hardware has to go and figure out where that parallelism is now. You could think of an alternative instruction set, which is not sequential, but instead is a graph of different dependencies like this. And people have built those sorts of machines. They're not very common. They're typically called data flow machines. And if we have time for it, we'll have one lecture about that at the end of the term. So there are machines that allow you to express this and this are not dependent on each other. And maybe sometime in the future, they do become dependent based on some branch or something like that. So you can think about that. But in a sequential processor, you need to come up with some ordering. And this is a limiter for these machines. So effectively, let's say the compiler optimizations, knows that this and this can execute at the same time. By definition, if it can generate this code, it knows those two things can execute at the same time. Unfortunately, it has no way to express it. And that's a bummer. Very long instruction word machines, which we'll be talking about a little bit in the future, allow you some ability to say, I want to execute, let's say, this and this at the same time, but it's very limiting. Data flow machines allow you to do much more complex sort of graphs of instructions and say, this is dependent, this instruction is dependent on this instruction, and that's all I really need to say. And so effectively, sequential machines have over-constrained our designs. OK, so let's start evaluating our first out-of-order, in-order machine. So I4, this is actually an in-order machine, but we're going to be analyzing it as a motivator and then sort of a slippery slope, if you will, into true out-of-order machines. So here we have fetch, decode, execute, memory, write back. Same 5-stage pipe. I renamed things a little bit easy to make it easier here. This actually follows the nomenclature that's in your labs, where the execute stage has an X and the decode stage is not ID, but instead D. But this should all look relatively similar. I took out all the sort of extraneous bypassing and other stuff in this pipeline, so it's a sort of caricature of a real pipeline. OK, so let's say we want to do superscalars here. Let's say we want to start adding multiple pipelines to this processor. So we're going to take the same processor pipeline, and we're going to split it off and have two pipelines here. We're going to have a memory pipe and an execution pipe. This looks similar to our A and B superscalar. But for today, let's focus on a in-order machine where these two pipes cannot have different instructions in the same stage at the same time. So we're going to look at a single fetch processor here, or a single issue processor, if you will. But this is a motivator. We'll see why we're doing this as we build up. It's a more complex out-of-order things. Most of these things hold actually for the multi-issue variants, but your head will hurt a little bit less if you think about the in-order variant, or the in-order single issue variants first. OK, as I said, yeah, things get a little more complicated. Let's take that same pipe that we had from before and add in a 4-stage multiplier. So now we have an execute stage, a single execute stage, which actually has some work in it. So this has an ALU inside of it. The memory, let's say, has 2 stages. This does the address computation. This is the actual memory access. And then here we have a multiply, which takes us a long time. It's pretty common. Multiplies are big, complicated beasts. So it's 4 stages of multiply. And then out over here, we have the write back. OK, so this gets us thinking. And we want to start to think what these things look like on the inside. So the first question is, do we want to bypass this pipeline? And how much pipelining, or how much bypassing do we need? In-order pipe, 3 pipes, or 3 functional units, we'll call it. 1, 2, 3. But we probably still need to bypass. Can we bypass out of right here? Out of Y1, does that make any sense? So the multiply is not done till here. So it makes no sense to bypass out of there. Do we need to bypass out of here? How about here? Here. OK, a lot of bypass locations. So this starts to, you can see the bypass exploding very quickly in this sort of pipeline. And that's pretty much to be expected. If you don't bypass, and you have to wait for everything, let's say, to get back to here, your clocks per instruction of your machine goes up. And we sort of go back to that simpler machine we had seen in earlier classes, where sort of you have to wait for instructions to go all the way to the end of the pipe. And that's a bummer. OK. Yeah, so that's what we just said. I did want to introduce this term, functional unit. So functional unit means one execution pipeline. So this is a multiply functional unit. This is the memory functional unit. This is the execute functional unit. OK, so now we're going to start introducing some extra structures and start talking about some extra structures, which will make our lives easier when we start to have multiple pipelines and complicated things are happening. The first thing I want to introduce here is the architectural register file, or ARF for short. So the architectural register file is where we keep the canonical state of the machine that has been committed. Hence, it's called architectural register file. If you see me say register file, that may or may not be an architectural register file. It may have in-flight values, but the architectural register file is the committed state of the machine. So we draw that sort of at the end of the pipe here, because that's where writes happen to this register, the architectural register file, as shown here by this W in the nice the nice pipeline diagram. We have W, and we try to read it at the issue stage of the pipe, or the register fetch stage of the pipe. I did want to say that when we went to go do this, we added an extra stage here. So we went to a 6-stage pipe because we're assuming that we bypass everything, and we want to have a little bit of extra time. And we'll see, for some more of the complex pipes, we'll start to put stuff in this decode stage. But for right now, decode does decode. Issue stage does some instruction steering to which functional unit, and not a whole lot more. So that's what's in our architectural register file. We read it here, we write it there. That makes sense. We may have to bypass some in-flight values around, but those are not in our architectural register file. Those have not been committed. Those are just in-flight speculative values. SB. So what's SB here? It's the scoreboard. So what does a scoreboard do? So we're going to show some pictures of scoreboards, but for right now, what our scoreboard is going to allow us to do is it's basically going to be a convenient side structure where we're going to keep track of where different values are in flight in these different pipelines. All of this data, if you go back to our earlier pipelines, was there. We had sort of the instruction registers that went down the pipe here, which in the control, which kept track of what was in each stage. The scoreboard is just a convenient place to put all that information and centralize it all. So when you go to build a pipeline like this, you don't want to have to go pick off of random locations in the pipe. It's easier just to sort of memoize that data in one location in the pipe, in the scoreboard. And when we start to go out of order, we're actually going to store some information in the scoreboard, which gets very hard to pick out of other locations. The scoreboard, read and write and write. What happens here? Well, we read it to figure out where we go get the bypass information from. So in this, we're not going to use that calculation we used before, but we're going to read it to figure out where the bypass information is coming from. And we're going to write it when we actually issue the instruction. So we actually issue instruction, we have to update some information in there. And then as the instruction goes down to the end of the pipe, if the instruction actually commits, we also need to do something in our scoreboard. If the instruction doesn't commit or takes an exception, we also will have to do something at the end of the pipe. We'll have to clean up the scoreboard. So let's look at a scoreboard. Here's our basic scoreboard. This is for a long multiply pipe, the pipe we just saw. And we're going to keep track per real register. R0 in MIPS is a dead register, so we're not actually going to, or a register which has no dependencies going through it, so we're not really going to talk about that. So P. So we have one bit in here which says if there's a write pending to that register. F, or functional unit, keeps track of which of the 3 functional units we should be going to pick off the value from. So this is important when we go to do the bypass calculation, what's going on. And then we're going to have a shift register for each register, if you will, where we're going to inject a bit and every cycle we're going to clock it forward. And this is going to tell us where to pick off the value. So this tells us which pipeline to look at out of 3, and the data available tells us in the other dimension what stage in the pipe to go pick off from. So if you go look at what functional unit you are and you cross it with this information, you should go figure out where to go do a bypass from. OK, so every cycle, logically, you can think of these bits shifting to the right. So it means the data, if there's a 1 here, that means the data for register 1 is going to be available in 4 cycles in the somewhere. Probably the architectural register file if you implement this relatively simply. Let's see, other things I wanted to say about this. I think we covered this all, yeah. So you need to use the functional unit and the data available fields to figure out when to bypass and where to bypass from. And then if the pending bit is 0, that means go look in the architectural register file. Do not go pick it off the bypass network. OK, now we get into a fun example, buyer motivating example that we saw at the beginning of class. So here we have that same instruction sequence we saw at the beginning of class. As we know, you can try to execute some of those things either at the same time or out of order. But for right now, we have an in-order, 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 in-order machine. But let's look at what the scoreboard has to say about this. So on the bottom of this graph, this chart, we actually show the scoreboard. And red denotes that the value is ready. So let's take a look at something here. So in cycle 3, we start executing instruction 0. Instruction 0 is a multiply. So what happens is, it was in, sorry, so I want to actually explain this. Here's cycles. D means what's in the decode stage of the pipe, what instruction number is in the decode stage of the pipe. I is what's in the issue stage of the pipe. So 0 on cycles, instruction 0, the multiply enters the decode stage, then goes to the issue stage, and then it moves to the execute units. So it actually gets put into our scoreboard. And what happens is it gets put in for register 1 into its scoreboard just for register 1, and that just marches down the pipe every cycle. So every cycle, it's going to move to the right. And now if you look at the pipeline, if you look at the functional unit, and you know it's a multiply, and you look at where it is in the pipe, you can say, oh, this is when that value actually becomes ready. So we now know exactly where in the pipe and when, or excuse me, which functional unit and when that value is ready by looking at the functional unit and the bits in the scoreboard. If we look at something, let's say next instruction here is an add, instruction 1, it moves here, and then it just goes down the pipe. And it's ready basically the whole time. We don't have to wait for this value to become ready, because the execute instruction, you can basically bypass out of the execute unit, and it's almost always ready. That's why it's read the whole way down. And you can sort of see here that register 1, this is when that scoreboard entry is valid. And this is when the register 11 scoreboard entry is valid in time. OK, so let's look at our first real read after write dependence. So here we have a multiply, which is dependent on R1. As you can see, that instruction is going to sit in the issue stage until Y3 happens, then that gets bypassed down here. Excuse me, it gets bypassed down here into the issue stage, and then that instruction can issue. If we go look at the scoreboard, that corresponds to this becoming red, And then we can go and actually issue instruction 2 to here, and we've basically bypassed that value. And register 5, which is the destination of instruction 2's multiply, is valid. So this is a relatively simple pipeline design here, or a relatively simple processor. But what's nice here is you can use your scoreboard to keep track of when things become ready without having to go, and which pipeline to go look in, without having to sort of look at intermediate bits in the pipeline. And it's going to become much more important as we go to sort of out-of-order machines. OK, before we move on, does everyone understand how to look at one of these diagrams? Because you're going to have to draw these later in the course. So this is a great question. So let's look at this picture here. So we only have one entry per location in the pipe here. So you're saying we only have one of these entries. We have multiple bits going down here, but we only have one entry here. So what happens if you have, let's say, things which issue to 2 different functional units with different latencies to the same destination register? So that's a very important question. What's going to happen is you're going to fill in with this functional unit the newest instruction that gets issued location. Because from a bypassing perspective, that's all you need to know. So that's very important. You don't need to know, from a bypassing perspective, something that was older in program order. We only need to bypass the newest value. One thing that we do need to do is make sure that we don't have a write after write hazard. So what that means is we're writing something later in the pipe than earlier in the pipe. That doesn't happen in this pipeline because we pipe everything forward. We don't actually have write after write hazards in the write back stage. The next pipeline we're going to look at does have a write after write hazard. And that's going to require us to think a little bit harder about the scoreboard. Exactly, yep. So we're going to have, that's sort of the next pipeline diagram, is we have a much more interesting scoreboard. Actually, two, not the next pipe, but the pipe after that is going to have a more interesting scoreboard. One interesting thing to note is strictly for what we've talked about today, you don't even need bits. You don't need to track 2 different writes to that same register. Because you only need to know the most recent write to the register. So one way that I've seen people build scoreboards is instead of having bits marching down here, you just have a encoding, like a log base 2 encoding or a binary encoding of where to go look in the pipe for the newest value. And then you just increment that or decrement it every cycle or something like that. So you just have, instead of having shift registers, you can have that. And that's strictly enough for this. The more complex pipes we're going to look at, as Pramod said, we're going to have to track both the location, or the functional unit in the pipe, and what stage in the pipe it's in. So you're saying, how do I know that this is not ready until 4 or something like that? OK, so that was a subtle point, is that if you know what functional unit, if you know the functional unit latencies, you just look it up in a table. You don't need to actually track that information. There's just some piece of logic which says, for a multiply, if the functional unit is multiply, then we can't bypass till here. If it's an add, we can bypass from here or there or something like that. So you don't need to track that in a table. It can just be part of your combinational logic in your decode unit or your issue logic. Does that, you don't have, I'll say it one more time. To see this, like this is this example here. We have a mul that writes R1 and something which else is supposed to read R1, but we end up stalling here. In this table, the way we know that is we know the functional unit. And because it says multiply, we know that we have to wait until it gets to here, or rather probably here, instead of trying to pick it off earlier. If it said ALU, then we could have it pick it off earlier. So we don't necessarily have to encode that. That's why in this picture here, things turn red on some of these earlier than others. It's that functional unit information which encodes that. You could even think about having that functional unit bits encoding some number, like you said. Some people design scoreboards like that. OK, so I just wanted to briefly introduce this, and then we're going to break. Next class, we're going to be talking about in-order front-end and issue, out-of-order, write-back and commit on these pipelines. It looks pretty similar, except some pipeline stages are taken out here. And this makes you think harder about when to go read the scoreboard. So we're actually going to use this decode stage to do some stuff with the scoreboard. And then we're going to start talking about truly out-of-order machines, where you have these other fancier structures like reorder buffers and store buffers. OK, let's stop here for today and pick up next time.